this lesson we're going to be talking about patterns and nonlinear functions. Well, if we're going to talk about nonlinear functions, we might as well at least compare them to linear functions. A linear function is a function whose graph is a non-vertical line or not part of a vertical line, but it is kind of in a line. So these are forming a line and they're not vertical or part of a vertical line, so those are all linear functions. Versus these are not part of a line. They are curved in some place, or they change directions in two different straight lines. Okay, so let's go ahead and look at classifying examples as linear or nonlinear. So here we have two sets of data, and we're trying to determine whether the sets of data are linear or if they are nonlinear. Well, you might grow to become good at telling just from the table if they are linear or nonlinear, but this is not the easiest way to make this judgment. The best thing is to actually go ahead and graph this data. So on the next page, we're going to go ahead and actually make graphs of these two pieces of data. Okay, so the pizza function, we're going to throw in some points. At 2, we are at 12.5, so about there. At 4, we are at 50. At 6, we are at 113, so right about there. At 8, we are at 201, so pretty much on 200 there. And at 10, whoops, look, I made a mistake, off one. At 8, we are at 200. And at 10, we are at 314, so right about there. So if we look at this data, it is not forming a straight line. We couldn't lay our ruler on it. It's kind of curving upwards in shape, so that's going to be nonlinear. Now if we go ahead and graph the sauce versus the cost function, for 2 ounces we're at about 80 cents. At 4 we're at $1.60, so somewhere in there. At 6 we're at $2.40. So maybe about there. 8, we're at 320. So probably there. And then 10, we're at $4. So to the best of my ability, I did draw those all in a straight line. Those are part of a line, so that function is linear. Forms a straight line linear. You can see the word line right in the name. Okay, let's look at another example. It says the table below shows the graph that shows the fraction A of the original area of a piece of paper that remains after the paper has been cut in half n times. Graph the function represented by the table. Is it linear or nonlinear? Okay, so the table's already been kind of constructed for you. After you cut it in half once, you have half, half again, you have a quarter, and then an eighth, and then a 16th. All right, so we'll go ahead and number this as 1, 2, 3, 4 cuts. And over here, I'm going to go ahead and count relatively small by eighths. So that's an eighth, and that's a quarter. That would be 3/8, and this would be a half. And then all the way at the very top line is 1 there. All right, so at 1 cut, we are at 1/2. At 2 cuts, we are at 1/4. 3 cuts, 1/8, and 4 cuts, 1/16. Again, this is kind of rapidly declining and will curve, so it is going to be nonlinear. To answer our question up here, nonlinear. Try that again. And will the graph ever reach 0? It's an interesting question. If you keep dividing in half and half and half, you'll get smaller and smaller and smaller and closer and closer and closer to 0. But no, you will not ever reach 0. Another way to think about that is think the numerator every time here has been 1. So because the numerator is always 1, it can't possibly be 0, because you'd have to have a numerator of 0 to give us a value of 0. But it's getting smaller and smaller and smaller. Okay, now let's go into graphing a function rule. So it's important that we can take an equation or a function rule, another way of saying it, and create data points and then plot them on a graph. So this first example says make the graph of the function rule y equals negative 2x plus 1. So here if we plug in negative 1, we get 3. If we plug in 0, we get 1. If we plug in 1, we get negative 1. If we plug in 2, we get negative 3. This third column here is set up to kind of help you construct an ordered pair. So the x value is negative 1, the y value is 3. Here the x value is 0, the y value is 1. X is 1, y is negative 1. X is 2, y is negative 3. Great, so we'll go ahead and graph those. So we have a point here, here. This part I'm sure you are all well comfortable at doing. So we're going to make those data points, and then to the best of my ability, try to draw a straight line through those. Not working out so well for me here on the graphics pad here, but these are definitely forming a straight line all the way down. Okay, what about the graph of this rule? If we plug in negative 2, we end up getting negative 2. We plug in 0, we get negative 1. We plug in 2, we get 0. We plug in 4, we get 1. So these would be the points negative 2, 2, 0, negative 1, 2, 0, and 4, 1. Okay, we'll go ahead and plot those points. Here's negative 2, negative 2, 0, negative 1, 2, 0, and 4, 1. Okay, those are forming a straight line there. Okay. Let's go ahead and graph some real-world examples here. So here we have the function W equals 146C plus 30,000 represents the total weight W in pounds of concrete. Mixer, the truck that carries the C cubic feet of concrete. The capacity of the truck is about 200 feet cubed. What is a reasonable graph of the function rule? Okay, so here we've got basically a setup counting up to 200 because that's a reasonable amount. And we're going to go ahead and plug in these different values. So we plug in 0, we're just going to get our 30 grand. We consider that maybe the weight of the truck. If we put in 50, for C, we're going to get a value of, 37,300. We plug in a value of 100, we get 44,600. If we plug in 150, we get 51,900. And if we plug in 200, we get 59,200. So we can make the ordered pairs 0, 30,000, 50, 37,300, 100, 44,600. I'm not putting the commas in the separating the thousandths place in the numbers just so it doesn't confuse us with where the comma between the x and y values or the c and w values are. Here are 150 and 51,900 and 200 with 59,200. Okay, so we can go ahead and graph this. We're going to go ahead and make 10,000 increments. So if you want to kind of put like 10 here and 20 here, we'll say that this is in thousands. And then 30, 40, 50, 60. And down here, let's count by 25s. I'm actually only going to mark every other one as 50, so 50, 100, 150, and 200, but we really are counting by 25s. Okay, so we start off the graph at 0, 30,000. We go up 50, and it's at 37, so we'll call that about there. 100 with 44, about in the middle there. 150 with 50, almost 52. And then 200 is just shy of 60. And we can see that those are actually a linear function that we just graphed going off that way. Now, you might actually not want to go past the last dot because they said that's kind of the capacity for it, so it maybe even stops right there. Great. Okay, so let's look at another example. It says the function rule W equals 8G plus 700 represents the total weight W in pounds of a spa that contains G gallons of water. What is a reasonable graph of the function rule? All right, given that it has a 250 gallon capacity. So let's start off with 0 here, and we'll go up by 50s, 50, 100, 150, 200, and I'm going to add 250. We could have maybe skipped 0, but I like including 0 there for our number's sake. All right, so if we put in 0, we're going to get 700. If we put in 50, we're going to get 400 plus 700 is 1100. If we put in 100, we're going to get 1500. If we put in 150, we're going to get 1900. If we put in 200, we're going to get 2300. And if we put in 250, we're going to get 2700. You might have noticed we were going up by 400 every time. All right, so our ordered pairs here would be 0, 700, 50, 1100, 100, 1500, 150, 1900, 200, 2300, and 250 with 2700. Okay, so for our, we have our G for gallons, and we have over here our W for weight. So our gallons we can count up. We have spots. Let's go ahead and go with, can't count by 25. That won't quite get us there. So let's go ahead and count just by 50s here. 50, 100, I'm going to skip, call that 200, and 250. Okay, and on this side, let's go ahead and count. We have 1, 2, 3, 4, 5, 6, 7 lines, and we have to get to 2700. So let's go ahead and make those 400, 800, 1200, 1600, 2000, 2400, and 2800. Okay, so 0 with 700. That's why I like that, so we can see it on the graph. 50 goes with 1100. 100 goes with 1500. 150 goes with 1900. 2000 goes with, 200 goes with 2300. And 250 goes with 2700. So again, forming a straight line, kind of connecting up there, but that's the capacities there, so we're going to go ahead and stop there. All right, so one thing that's important to talk about when we're making graphs of real data is whether the data is continuous or discrete. Continuous means the data is not broken. Discrete, it is broken up into small pieces. Basically, if there's points in between points, like so if I said here's a point and here's a point, there's actually points in between. And if you made enough points in between points, it actually just kind of forms a whole line of points. Imagine zooming in way down, and you'd find that there's countless points in between points. Here, there aren't points in between those points. We can't break something down any smaller. So we'll talk about why that might be. Why might we not be able to break things down any smaller? Okay, so if we think about this first example, we have a local cheesemaker is making cheddar cheese to sell at a farmer's market. The amount of milk used to make the cheddar cheese and the price at which he sells the cheese are shown. Write a function for each situation, graph each function, and is it discrete or continuous? So if we think about this, the first example has gallons of milk and ounces of cheese. So we can go into like fractions of ounces and fractions of gallons. So we can keep breaking those down into smaller and smaller pieces. So this data is going to be continuous. Now, the other example, each wheel of cheddar cheese costs $9. We're not going to continue to break this down smaller and smaller. You maybe can find a grocery store that sells you part wedges of cheese, but each wheel is going to be probably one amount, and that's sold for $9. A half wheel might not necessarily follow that same pattern. So we're selling wheels. We can't really break those down. So that's discrete data that you can't really divide into pieces because it's not the same anymore. So a wheel of cheese isn't the same as a half of wheel of cheese. Okay, so here we have space to graph these. When we go ahead and graph continuous versus discrete data, as we saw above, we're going to get a little bit of a different result here. So I'm going to go ahead and throw some data on here, some scales on here. All right, so 1 is 16, 2 is 32, 3 goes with 48, and 4 goes with 64. So however many gallons we have corresponds to how many ounces of cheese we make, and we can connect those with a nice solid line because we could really make any amount in between there. Okay, this is gallon and ounces here. But over here, when we go ahead and graph this data, we can't necessarily do that. Those are the wheels of cheese we have, and here's the amount of money we're making from them. I'm making a very convenient scale just to make this quicker. So we've got money over here and wheels of cheese down here. So 1 costs $9, 2 costs $18, 3 costs $27, and 4 costs $36. And this could even consider, continue, but in between here, 2.5 wheels, we don't know how much that costs. We're not going to connect those points. We're just going to leave them as individual discrete data points. So we kind of talked about that up there. The first graph is continuous, the second graph is discrete. All right. The amount of water W in a wading pool in gallons depends on the amount of time T in minutes the wading pool has been filling as related to the function W equals 3T. So let's go ahead and graph that data. So I'm going to go ahead and actually try to pick something more realistic. So I'm going to pick like every 10 minutes. So here's time in minutes. So that's 10, 20, 30, 40, 50, instead of just counting by ones. And over here, I'm going to count by 25s, but I'm going to mark every other line as 50, 100, and the top will be 150. All right, so if we're given by this rule, if we plug in 10, we get 30, 20, we get, oops, I'm sorry, that's not the right spot, right about there. 20, we get 60, 30, we get 90, 40, we get 120, and 50, we get 150. So over time, it's not going to be like the pool just jumps up to 30 gallons in it. It's going to slowly increase all the way. So as time's going, little by little, that water is filling. So that is continuous data going up, up, and up, and up. Now here we have tickets bought, and we have the cost. So since you don't really buy one ticket, let's go 2, 4, 6, 8, and 10. And over here we'll count, counting by 30 should work, 30, 60, 90, 120, 150, 180. Now, most baseball stadiums don't sell parts of tickets, but 2 tickets cost about $32, 4 costs $64. 6 is going to cost 96 there. 8 is going to cost right about there, and then 10 will cost us $160, so right about there. Now, should we connect those points? Well, they're not going to sell us parts of tickets. While we could certainly find the price of one ticket in between, we could find like 1 point in between, but we can't find all the points in between. Those don't exist. You don't get parts of tickets, and they certainly don't cost you a smaller portion of money there. So that data is discrete. Okay. Now we're going to look at graphing nonlinear function rules. So here's a function. It's got the absolute value symbols in there. So it's taking the absolute value of x and then subtracting 4. So let's go ahead and make a table of values. So we plug in -2. The absolute value of -2 is 2. 2 minus 4 is -2. Absolute value of -1 is 1. Minus 4 is going to give us -3. Here we get -4. We get -3 again. That's interesting. And then -2. So if we go ahead and plot these points, we get -2, -2, -1, -3, 0, -4, 1, -3, and 2, -2. All right. So if we go onto our graph here, our first point here, -2, -2, and then -1, -3, and then 0, -4 is looking linear, but then the next point's weird because it's 1, -3. We start to come back in the other direction. So next year you'll spend more time focusing on graphing absolute value equations, but they kind of look like V's like this. And even though each piece is linear together, the whole graph is nonlinear. You need to be one straight line, not two straight lines. Okay, let's do another example. Let's go ahead and graph y equals x squared plus 1. All right, plug in -2, -2 squared is +4 plus 1 is 5. We get 2 if we plug in -1, 1, 2, and 5. You might have noticed a similar pattern to before. So that's -2, 5. That's -1, 2, 0, 1, 1, 2, 2, 5. So go ahead and graph this. -2, 5, -1, 2, 0, 1, 1, 2, 2, 5. So you can't put a perfectly straight line through these. So let's connect these with a nice smooth and curved line. Yours is going to look better than mine drawing on the computer here. It should kind of get rounded at the bottom there and then come back up. Okay, so do your best to make that round at the bottom because that's really what this graph looks like, but definitely not linear. An interesting shape here. There's a special name for it that you'll learn about next year. It's called, sneak preview, a parabola. All right, so another graph is if we have x cubed plus 1. So careful, when you plug in -2 cubed, you do get -8 plus 1 is -7. Then we get 0, and then 1, 2, and 9. So this does go off the graph a little bit. The points that we can find space for are right here, and you might be actually inclined to think, oh, that looks linear. But the next point is way up here for this side, and down here a bit over on this side. So this graph actually kind of looks like an S. Try my best. And we'll practice more of those, but again, definitely nonlinear. So from there, you can go ahead and try the examples in the homework on pages 29, 30, and 31.